for the satellite and the ground station. Here's just a summary of what I just said. The EIRP can be very high. The free space loss, it's also something which is very high. The received carrier power can be very, very low. Sometimes it's picowatts, and therefore the logarithmic representation is advantageous. So now we can take what we have developed so far, the same formula, which you have seen before by a multiplication and division, is now translated into C over n equal, this is just the proportionality factor, 10 log transmit power plus 10 log transmit antenna gain. Here we had the square, 4 pi r over lambda square, if you remember. So the power can be put up front. So we have 10 times 2, so therefore here's the factor 20. 20 log 4 pi r over lambda plus 10 log the receive antenna gain. And because the other stuff is divided, so here we have a minus. 10 log system temperature minus 10 log Boltzmann constant minus 10 log the bandwidth. As you will see later on, so this is the free space loss. So this is a very simple link budget. More losses will come up a little bit later. Yeah? But this is the predominant loss here. So in dB, our signal to noise ratio is the EIP in dBW. So we refer to 1 watt. Sometimes people do it, refer it to 1 milliwatt. So then it's dBm. And the difference between the two is 30. Yeah? So because it's a factor of 1,000, and the factor of 1,000 is 30 dB. Factor of 10 is 10 dB in power. And factor of 100 is 20 dB. I mean, these are a few things you should be able to do without any calculator, without any notebook. A factor of 2 is 3 dB, a factor of 4 is 6 dB in power. Yeah? Okay. Quite useful sometimes. With my students, quite often, I say when there's an exam and they do some link budgets, and I say, well, there's always the possibility to make some mistake, some error. But if at the end of your link budget, you write down that the signal to noise ratio is 325 dB and you leave that uncommented, then you get 0 points. Yeah? So, because this is unreasonable. Yeah? So, probability and check for whether this result makes sense is always advisable. So, basically, our signal to noise ratio is given by the EIRP of the ground station. I mean, the free space loss is given. Yeah? So when we choose the frequency and when we have the distance, I mean, here we can't do anything about. But there are 2 parameters in our ground station, or when it's going from ground to satellite. Here we can fiddle around. Yeah? So we can improve the figure of merit either by having a higher gain antenna or a better amplifier with a lower system temperature. Yeah? And this is the other parameter, the bandwidth. Yeah? So if I reduce the bandwidth, then I inject less noise and I improve the signal to noise ratio. I mean, this is in satellite communications a state-of-the-art method. If there is additional attenuation due to fading, yeah? Weather effect, it's raining heavily, then, I mean, that's there. I mean, we can't do anything against physics, but we can take some countermeasures. And by adaptive transmission, a very simple way would be that I reduce the bandwidth. Yeah? And this way, I improve the signal-to-noise ratio again. Of course, the other possibility would be, in this case, I increase the power. So uplink power control is a very traditional way of doing that. And again, I can get to a healthy link budget. Sometimes you find this figure, signal power versus noise density. Again, mathematicians wouldn't like that very much because this is power and this is energy. So I'm comparing 2 things, but in the end, you will always calculate the dimensional signal to noise ratio. Basically, this is just normalized to 1 Hertz noise bandwidth. So we take EIRP minus all the losses plus the figure of merit, and we subtract the Boltzmann constant here, which is expressed in dB joule per Kelvin. So that's the proper dimension. Sometimes you also find an even more strange relationship, C over T, carrier power versus temperature. So basically, we have left out the Boltzmann constant. And when you calculate in a transparent transponder, uplink and downlink. Yeah? So the bandwidth and the Boltzmann constant is the same both ways. Yeah? And therefore, I mean, in the intermediate calculation, you leave it out, and in the end, you take it into account, and then it's again correct. So this would be just simplifying the intermediate calculation. In digital communications, a very important figure is the energy per bit over the noise density, EB over N naught. And the, let's say, quality criterion for a digital communication system is the bit error rate as a function of EB over N naught. Yeah? Why EB over N naught? We have learned C over N, we could do that. Cautious. The point is, we must avoid that we compare apples and pears, yeah? Because in an uncoded system, the information rate and the bandwidth on the channel are the same. However, when we put on redundancy by forward error correction coding, then the information rate and the channel rate is different. Yeah? So for instance, if for every bit I add a redundant bit, I have twice as many bits on the channel than information bits. Yeah? And in order to compare performance, I have to normalize. And this is a normalization process that the energy per bit is carrier power divided by information rate, and noise density, also an energy, is the noise power divided by the equivalent noise bandwidth. So it's C over N times B over R. Yeah? So this I can measure, this I can measure immediately with a spectrum analyzer or with a power meter, and then if I want to know the EB over N naught, then I multiply by Bn over R. But I put that in red. Very important, this is the information rate of the user bits in the end, not the channel bits, not necessarily the channel bits. So, just to give you some examples with some numbers, let's say our ground station transmits with 10 watts, and we are feeding this in a quite long UHF Yagi antenna with 18 dB gain. Then we have an EIRP of 10 log 10 plus 18, so this is 28 dBW or 58 dBm, and this corresponds to 631 of watts of EIRP. So if I would have an omnidirectional antenna, I would have to feed more than 600 watts into this antenna to get the same effect at the spacecraft. Yeah? Obviously, this is not the most economic way, because we would radiate in all directions, and we just need the power in one particular, very narrow direction. Any questions so far? Okay. Now, let's calculate what is the free space loss. And I'm assuming here 1,000 kilometers between the ground station and our little spacecraft. We are transmitting at 438 megahertz. The wavelength can be easily calculated. This is the speed of light, 3 times 10 to the power of 8 meters per second, divided by the frequency, 438 times 10 to the power of 6 hertz. Take care of the dimension. So this is, if you mix up kilohertz, megahertz, hertz, you can get several orders of magnitude wrong. So everything should be done in meters. I mean, you all know the story. I mean, there had been a loss of a complete mission because meters and yards were mixed up. So there's a difference. Yeah? So then the free space loss here is 10 log 4 pi r over lambda square, or 20 log 4 pi r over lambda. So in this particular case, we have 20 log 4 pi million meters divided by 0.68 meters wavelength, and this yields 145.3 dB of free space loss. That's a lot. Yeah? So this is 10 to the minus 14 of the original power. Yeah? So we get a very, very weak signal at the input of the satellite. I mean, if we have a geostationary satellite, then, for instance, if we would go to Ku band, 14 gigahertz, that would be 207 dB of free space loss. Yeah? And if I would go to 30 gigahertz and go to a geostationary satellite, I have 213 dB of free space loss. Next example, let's go to S-band, 2.4 gigahertz, wavelength becomes smaller, 12 centimeters. Same distance, when we insert that, then you see we have 160 dB of free space loss. Next example, let's go to X-band, 8 gigahertz, then we have 3.7 centimeters of wavelength, and then we are at 170 dB of free space loss. So this has to be borne in mind when we want to go to higher frequencies. They are advantageous because there is more bandwidth available, but there's a penalty for that. It's free space loss. On the other hand, if our transmit antenna on ground is a dish, if we go up with the frequency at the same size of the antenna, the gain of this antenna increases with the square of the frequency. Yeah? So the two things cancel out. Yeah? So the free space loss and the additional gain of the antenna, they compensate. Unfortunately, what does not compensate, we have propagation effects. And the higher the frequency, the more pronounced the attenuation due to the atmosphere will be. And this is a function of rain. In clear weather, it doesn't matter. But if we have rain, then we are penalized at the very high frequencies. Huh? I mean, at UHF, this is negligible. Even at S-band, it's not very pronounced. But when you go already to X-band, then you have to be a bit cautious. Yeah? And it depends also where your ground station is. So for instance, if you are in the tropical belt where you have extremely heavy rain, then you may have a problem. And you have to put in sufficient margin. I mean, this comes at the end. You have to put in sufficient margin that even in the case of severe rain, you have still a proper signal-to-noise ratio so that you can communicate to your spacecraft. So here, actually, I forgot here, that should be 2000. Here I have inserted it. So if the distance increases to 2000, I mean, we have a 6 dB increase of the free space loss. Again, when you design your link, then you have to do it for the worst case. Yeah? So the longest distance just when the spacecraft arrives on the radio horizon. Now a little bit about receiver design. It's very basic. So let's assume we have an antenna and then we have an amplifier. So the antenna will pick up noise from around. So we have a certain noise density, which is K times T, via the antenna. And then the output of that, we would amplify that. The noise density at the output of the receiver will be the noise of the antenna plus the noise produced by itself times the gain. And when we relate that to this as a reference point, then we divide by G. And therefore, we have at the input a noise density, which is K times T antenna plus T, if T1 is the noise produced, temperature of the receiver itself. Now, let's put another receiver there. This has a certain temperature T1 and a gain G1. And then at the second amplifier, the output